Hello and welcome to my channel. In this video, we are going to understand how do we prove that a given mapping is a linear transformation. Now, in order to understand what a linear transformation is, let's take an example of two vector spaces V1 and V2, which have a mapping between them. Here, we shall assume that U and V are vectors in the vector space V1 and A is a constant or a scalar from the scalar field F. Then what happens is T of AU plus V, right? So AU plus V is a linear combination. This would be resulting in A times T of U plus T of V, right? Okay, now in our example, we have got V1 as V3R and V2 as V2R. So V3R is the vector space consisting of all three-dimensional real valued vectors, and V2R is the vector space consisting of all two-dimensional real valued vectors. Cool. Now, the transformation that is given to us, the mapping rather given to us, if you look carefully, the first and the second coordinates of the input is giving us the first coordinate of the output, right? And the first and the second and the third, pardon me, the second and the third input, the coordinates of the input are giving us the second coordinate of the output, right? Okay, so without much further ado, let us assume a u and v. So let u equals u1 comma u2 comma u3 belong to our v3r, right? And let v equals v1 comma v2 comma v3 belong to v3r again. So we have chosen two vectors from our domain, and of course let a be the scalar from our field r. Okay, now T of U is same as T of U1 comma U2 comma U3, and this would be the first plus second, that is U1 plus U2, and then second plus third, that is U2 plus U3, right? So we are following the formula given in the second line of the question, as you can see on top of your screen. And TV would be T of V1 comma V2 comma V3, and that would be the first plus second, that is V1 plus V2 comma V2 plus V3, right? All right, now we will find out what A U plus V is in our problem. So AU plus V, AU plus V is A multiplied by U1 plus u1 comma, so this is a scalar multiplication going on here. We will conduct that same thing in the next step, plus v, that is v1 comma v2 comma v3. The scalar multiplication goes as follows: au1 comma, pardon me, au1 comma au2 comma au3 plus v1 comma v2 comma v3, right? And then we are going to go for a vector addition, that is AU1 plus V1 comma AU2 plus V2 comma AU3 plus V3, and that gives us AU plus V. Now what we'll do is we will start off uh, our proof by using by writing down what we mean by TAU plus V, right? As you can see on the top right corner of the screen, we should be getting A times TU plus TV. Okay, now let the manipulation start for us, right? Let us get some good amount of white space on the screen. So this gives us T of AU1 plus V1 comma AU2 plus V2 comma AU3 plus V3. Correct? Okay. Now let's write this down in a more in our format, right? So AU1 is the first one, AU1 plus V1 is the first term, pardon me, and then we have got AU2 plus AU2 plus V2 as the second coordinate, right? And we have AU3 plus V3 as the third coordinate, right? So I have just color coded them so that it becomes very easy in the next step, right? Okay, so this transformation mapping as we had defined previously goes as follows. The first coordinate is going to be the first plus the second. So AU1 plus V1, oops, pardon me, AU1 plus V1 plus, right? And then we have got a plus over here, plus the second one. What is the second one? The second one is AU2 plus V2, right? So I'm using colors to identify which is the first one and which is the second one. Now, the second coordinate here, this entire thing that we have written here is the first coordinate, right? Then we give the comma now. The, the second coordinate is the second coordinate from the previous vector, that is AU2 plus V2, and then we add that with the third coordinate of the input vector, which is AU3 plus V3, right? So I hope that this representation over here is clear. Now what we do is we will write down the U's together and the V's together, right? We'll just rearrange. We're not going to do anything profound. We're just going to rearrange this as AU1 plus AU2 plus V1 plus V2, right? Comma AU2 plus AU3 plus V2 plus V3. So we have just rearranged our terms over there. And now we are going to write this as a sum of two vectors, right? So what we basically do is we'll take AU1 plus AU2 from the first coordinate and AU2 plus AU3 from the second coordinate and group them together. And at the same time, that would be the first vector, right? And the second vector, we would want that to be V1 plus V2 and V2 plus V3. Well, there are other ways to prove as well, but this is what starts from the left hand side and gives us the right hand side, right? So what our plan was as follows. What we are going to do is we are going to write this as AU1 plus AU2 comma AU2 plus AU3, right? This is the first vector plus the second vector, right? So the second vector would be V1 plus V2, comma V2 plus V3. We are nearly done actually, but we just need one small thing to be done here, right? So you can see very carefully that there is a associated with each term in the first vector, right? So we are going to take this a out, and that would give us the following. That would give us a times, in sky blue, I'll write u1 plus u2, comma u2 plus u3, right? And then plus v1 plus v2, v1 plus v2, comma v2 plus v3, right? Okay, now I think we are done. What have we got here, right? So let's try to identify whether we have got the correct thing or not, whether this is a of tu plus tv or not, right? So look at this very carefully. At the top of your screen, I'm mentioning something as 1 and something else as 2. So those are what we mean by tu and tv, right? So if you look carefully, the first bracket over here is basically tu, right? And the second bracket over there, maybe I'll use a different color pen over here. So first bracket is tu, right? And the second bracket is tv. Exactly, we have we have got the relation that we were longing for, right? So what we can write here is therefore T of AU plus V is equal to A times T of U plus T of V, right? So therefore T is a linear transformation, linear transformation. And that ends our beautiful proof over here. Okay, so basically we started off with two vectors, two arbitrary vectors, right? Arbitrary means they have been chosen without any condition. We have just said let U belong to the domain, let V belong to the domain, right? And we also chose a scalar, and we have proved that the linear transformation of U and V, which is given by AU plus V, is basically A times the transformation of U plus the transformation of V. Okay, thank you so much for watching the video.